Hello, everyone. Welcome to another session of the Kent Seminar Series. Today, we are delighted to have Professor Scott Moura with us. Professor Moura is the Clare and Shen Endowed Distinguished Professor in Civil and Environmental Engineering, Director of Energy Controls and Applications Lab, PATH Faculty Director, and Chair of Engineering Science at the University of California, Berkeley. He received his bachelor's degree from UC Berkeley and master's and PhD degrees from the University of Michigan Ann Arbor, all in mechanical engineering. From 2011 to 2013, he was a postdoctoral fellow at the Keimer Center for Control Systems and Dynamics, University of California, San Diego. In 2013, he was a visiting researcher at the Centre Automatique in Mainz, Paris Tech, France. His research interests include control, optimization, and machine learning for batteries, electrified vehicles, and distributed energy resources. Everyone, please join me in welcoming Professor Moura.
All right, thank you for that kind introduction. I am delighted to be here. I'm glad to see so many young people in the audience. I'm sure many PhD students and postdocs and the like. My first time at UIUC was coming as a prospective graduate student when I was an undergraduate, and there was some multiverse out there where I would have gotten my PhD here, and I'm sure would have loved it. So it's really good to be back. So let's go ahead and get started. There we go. Okay. All right, so let me first introduce my laboratory called ECAL, the Energy Controls and Applications Lab. So my own training is in control systems and dynamics optimization. Today, this falls under data science. If there's any investors in the room, it's AI. In a telescoping set of applications at the smallest scale batteries, we do algorithms models. One level up, we have vehicles that are automated, connected, electrified. And then one level up from there, we think about how actually transportation systems integrate with power systems and electricity markets. Now, I'd like to tell you our number one product. Our number one product is people. It's the students that we graduate, and this is our current research group, so you can see their faces and some of their names, and these are our alumni. So I'll just leave it here so you can see, their names and the types of organizations they go into after they've graduated. So this is our number one product, and the most important thing I think to pay attention to when it comes to what we do in my own research lab. I am also faculty director of PATH, which is something like it's a research center within UC Berkeley's Institute of Transportation Studies, which is something analogous to ICT here. And PATH, California Partners for Advanced Transportation Technology, our mission is to realize safe, equitable, efficient, carbon-neutral transportation systems for all through research and development of advanced ideas and technologies. But to give you a more clear picture, let me say something about our history and then our present and our future. So it has quite a history. Some of you may be aware, some of you maybe not. Let me start with the year 1997. So actually, PATH plays an important role in automated vehicles. We were the first to deploy automated vehicles on public roads with this platooning that you see here on I-15 highway just north of San Diego. And actually, I should emphasize, the point of this wasn't that the vehicles were intelligent and automated. It was actually the highway, right? So we can have more discussion on that history. Another piece of history is PATH was the first to create infrastructure-based traffic monitoring with a system called Performance Measurement System, which collects real-time data from 40,000 road sensors. The way we used to monitor traffic was like this. There are many younger people in the audience here, but the way we used to monitor traffic is we point a camera at the highway and we say, look, traffic. And the problem was, if we didn't point camera at the highway, we didn't know what traffic was in that segment of highway, right? Then the next transportation innovation was helicopter, because then we put camera in helicopter, and that helicopter moved around the cities, and you could see where traffic was, right? So this was infrastructure-based sensing, and it created this online platform where you could get real-time traffic measurement all across California. And then there's mobile millennium. So the way that most of you probably understand what the traffic is like is with your smartphone, like Google Maps, Apple Maps. So that was actually invented in Path before Google Maps and Apple Maps with this project called Mobile Millennium, started by Professor Alex Bayan, shown there, where he hired eventually ended up hiring 100 students to just drive vehicles along the highway. And the idea, of course, was using cell phones as sensors with the biggest cell phone company at the time, not Apple, there's no iPhone, not Samsung, it was with Nokia. Yeah, you remember playing Snake and, okay, yeah, okay. You guys look young, but maybe you're not so young if you played Snake on Nokia phones. So, and then after this was done, actually, seriously, a year after this, Apple hired basically the whole team, and Apple Maps traffic is like Path 2.0 software. Of course, it's evolved since then. And then more recently, we started this industry consortium, I guess it's been 8 years now, working on computer vision and AI technologies for automated vehicles. And today, here's some of our featured projects. I'll talk about NEXTCAR in this lecture. Mega Vander test. This was Alex Bayan and others. Actually, Dan Work was a big part of this, a former UIUC faculty member. Largest traffic experiment in history to use connected vehicles to suppress stop-and-go waves. We have a connected vehicle test bed we often work with. We work with the California Department of Motor Vehicles. Anyone been to San Francisco and seen these robocars drive around? Yeah? Did you take a ride? You didn't take a ride? Waymo, you tried? So, okay, you tried? Okay, so we actually do, we're the only research institute that has a contract to do analysis with the Department of Motor Vehicles to assess safety and various other things related to rural communities for freight and also for disabled and vulnerable. So here are just some of our faculty and researchers that are affiliated with the center. So, you can look out for these folks, and if you're interested in connecting with any of them, let me know and I can facilitate that. Another thing I want to emphasize about Path is here's how I see it. I see it in terms of these technology readiness levels. If you're not familiar, this is a scale, TRL, created by NASA to assess the maturity of different technologies. TRL1 is like, man has just observed this, right? When I was driving here, I was listening to a podcast about the scientists involved in Manhattan Project, and they're talking about trying to figure out the existence of neutrons because the atomic weight of atoms was more than just the number of protons. And anyways, that's TRL1, right? Okay. And then TRL9 is like iPhone. So Path, the role it plays, and I'm actually curious to hear from you if ICT, you see it similarly. Faculty and their research labs are basically at TRL 1, 2, 3, right? And then when they mature some idea and they want to take it to the next stage of maturity, then that's where you get to TRL 4, 5, 6. Sometimes we call this the valley of death, right? And then if it survives and matures, eventually industry picks it up for full deployment, commercialization up here. So I see Path's role is to basically pick up and help mature university research from faculty to the next stages towards demonstration and deployment. And important to that is partnerships, so the P of Path, with government, industry, startups, academia, because you need that to create these demonstrations and deployments. Okay, let me now mention some projects I won't discuss in detail, but I think there's different folks in the audience that might find this interesting and relevant. The first is a startup that came out of my lab called WattTime. WattTime, and they spun out a product called Climate Trace, basically does, they're a smart meter for carbon emissions. So much of my work is centered around reducing carbon emissions, particularly in transportation, but you need to be able to measure carbon emissions. So Climate Trace, you can go to climatetrace.org, and it's a map in a free database where you can zoom in with GIS into any place in the world and understand carbon emissions of facilities, right? And this actually was supported by Al Gore, the former vice president. Maybe you know in a COP, the Conference of the Parties that was in Paris, one of his big pain points was he got all these governments to agree on carbon emissions, but they had no way to actually measure and enforce it. You know, governments would just claim, right, what their carbon emissions were. So finally, he came across this startup that came out of our lab, which got funding from Google to use satellite imagery and AI to basically estimate where carbon emissions is. And then he kind of really helped supercharge it. So you can get something like this here. What I did is for the world, there's categories. You can break it down in visualizations of carbon emissions in different sectors of transportation here. Here, what I did was I picked two regions, North America and Asia, sector transportation, and you can see in each of these regions in transportation, what are the facilities that have the most amount of carbon emissions. So you can check that out if you're ever curious about carbon emissions. I mentioned these, you know, Waymo and the like in San Francisco. So what happens is actually these companies are required when they get a testing permit in California to submit crash reports. And so PATH researchers and PhD students do analysis on the safety of these AVs. So here's a question. Are these AVs as safe as human-driven vehicles? How many think those AVs in San Francisco are as safe as human-driven vehicles? Yeah, you have your hand raised. How many think maybe human-driven vehicles are safer? Yeah. Okay. Well, anyways, actually, I'm not going to give you a clean answer to this because there really isn't a clean answer. But if you want to know more, you can check out this TRB paper. But here it basically does an assessment of these AV vehicles in different stages versus Uber trips driven by humans, of course, right? Also in San Francisco. So we do this sort of analysis, and this visualization down here shows where vehicles are damaged. Actually, AVs disproportionately compared to human-driven vehicles tend to have more rear-end collisions. So the nature, the distribution of types of crashes you have with AVs are different. You can ask me questions to dive more. Something else we worked on is battery swapping. So we want to electrify heavy-duty freight transit, but doing it with these mega chargers, you know, might not be the best idea. So here we looked at this idea of what if you could swap the batteries in and out for trucks. Meanwhile, these battery swapping stations, when they're waiting for a truck to come in and take a charged battery, they basically serve as battery storage systems providing grid services. So this is an example now of when you electrify mobility, you know, the energy and transportation infrastructure are definitively coupled. Basically, this facility has two products, e-mobility and then power system services. And then this actually is very connected with the work of Professor Ria Cantu and others, where there was this California project that we have with different UC campuses where we asked this question. So in 2035, the plan is to have 100% new vehicle sales in California be all zero emission vehicles, largely EVs. But what happens when there's a disaster? How do we evacuate certain areas? So much of this is about vehicle routing problems in cases where you've got transportation links or power lines that are down, and how do you robustly evacuate people efficiently, and then planning of how you might place like mobile storage, mobile charging units. Okay, and last thing I'll mention is this coupling. We've also done some game theoretic analysis of these bipartite graphs of transportation and power networks. When you electrify, they couple, and we study equilibria of these types of systems. All right, so you can ask me questions about that, but I won't say any more about those projects. I want to now dive into the meat of the talk. So why electrified transportation? Many of you are probably convinced, but I'm going to give you my perspective. So if there's one number to give you, if I give you a quiz question after my lecture, here's quiz question number one, okay, is how many tons of greenhouse gases are emitted per year on Earth? And the answer to that quiz question is 51, okay, 51 billion, right? So when we think about when we're taking different sorts of actions in an effort to bring this to net zero, you know, how big are these slices? So here we're in this Institute of Transportation. Worldwide, transportation is like 60%. Many of you are doing materials research, right, related to transportation infrastructure. Look at this. 6% from cement, right? Huge opportunity to decarbonize if we can focus on decarbonizing cement, iron, and steel. I won't say any more about that. I'm just saying, right, is that there's a huge opportunity there. Now, this is worldwide, but it's not necessarily representative of more developed economies, right? This is the entire world. Let me focus on California because I'm in California here. So California, you know, is an example of like if it's own country, I guess it's the 4th or 5th largest economy in the world. Anyways, California emits 0.42 billion tons of greenhouse gases. Almost 1% of the whole world's greenhouse gases are because of these Californians. Damn Californians. So anyways, but the nature of California's economy, and there's very similar in developed economies, transportation is by far the biggest sector, 40%. So a lot of policies in California are very focused on decarbonizing transportation because that's a huge chunk, right? And then meanwhile, there's once you electrify transportation, you also have to electrify electricity, and that's also happening. Now, focusing on transportation for a sec, I love this graphic, although it's a little hard to read, from the Intergovernmental Panel on Climate Change, where they looked at emissions intensity. So that's the x-axis here for different modes. Okay, intensity. So you've got modes like air, maritime, rail, and road. And then this horizontal axis, emissions intensity, means CO2 per kilometer. Okay, so normalizing by distance, but also per passenger if you're moving people, or per ton if you're moving goods. So per passenger is blue, and then per ton is the orange here. So you can see air is the most carbon intensive way to move. So I flew here on a short haul 737 from Pittsburgh yesterday, and that's like the worst way emissions wise. So as much good as I'm doing maybe in research, I'm probably canceling it out with, okay. So anyways, but freight in particular is very, very emissions intensive. Road, light duty vehicle, heavy duty vehicles are much more carbon intensive. Yeah, so if we're trying to focus on what are the problems to focus on with a goal towards getting to net zero, I'm going to highlight these heavy duty vehicles. There's a lot of bang for the buck, of course, in terms of reducing carbon emissions. So zooming in, you can see that a bit more. You know, light duty is something less. Just putting people in buses already does a lot, so on and so forth. Moving over to rail and maritime also helps substantially, even just simple mode switch. Okay, now I'm going to tie this to power systems, and I'm going to be a little California specific. I'm going to talk about something called the duck curve, okay? And here's what the duck curve is. So here you have 24 hours on the x-axis, and on the vertical axis you have net power demand in megawatts. It's the net power demand for the entire state of California. Now, net means total power demand for the whole state less renewable supply. Okay, so what that means is this curve, basically as a controls person, this curve is basically like a reference that you have to track with thermal generators like nuclear, coal, natural gas. You need to schedule their generation so that they match this net demand. All right. Now, okay, what's going on here? This is a picture from 2012, and California was debating, do we have a policy to have 33% renewables by the year 2020? And so basically, much of the renewables comes from solar. And so here they were just projecting forward from 2012 to 2020. As you add more solar, right, it subtracts off more from demand, and the belly of the duck gets fatter and fatter. See, it kind of looks like a duck. Yeah. And, you know, so this is the nature. But here's the whole point of the duck curve. The whole point is right here, is this rapid ramping, where these thermal generators need to increase their power output very quickly. In this case, 13,000 megawatts in 3 hours. I think here in the state of Illinois, we have quite a bit of nuclear, right? And coal. So both nuclear and coal, some natural gas?
Natural gas, nuclear mostly.
Nuclear mostly?
51%, yeah.
61.
51.
51.
And coal
Thank
is
you, Ron.
around 20.
Got it. So we got nuclear, thanks for the numbers. Nuclear 51, coal 20. Both of those types of generators cannot ramp up and down quickly to do this whatsoever. Okay? So that's a big problem now. How are we going to integrate these renewables when we can't get, because they're variable, demand is variable, and we need some firm, flexible resource to balance, right? So that's a big problem. Now, that was in 2012, projecting to 2020. The year is 2024 right now, right? So what happened? Here's what happened. So in spring, this is actual data from California. So you got total demand with this light blue curve, and then this dark blue or purplish is net demand. So you can see the duck curve happened. It's kind of this big valley. And the ramping here, I picked a date in April this year, 16,000 megawatts in 3 hours. It's happening, this rapid ramping. In fact, there's even negative demand, which means, at least in California, in spring especially, we're generating more electricity from renewables, particularly, than we can even consume. We're over-generating. Okay? Now, and that's demonstrated because here, this green curve, it's a little hard to read, but this is renewable generation. You can see it looks like someone took like a knife and kind of sliced the top of it, right? Normally, you would have this type of shape. Because we have to actually reduce output from solar because we have nowhere to put it, right? We're trying to export it. Meanwhile, California is deploying all these batteries, and that's what this light yellow curve is, and they're trying to charge them up in the middle of the day, okay? By the way, I haven't been talking about transportation in the past couple slides. So you can kind of see, okay, now there's this opportunity where, maybe we can take all this excess supply and we can use it for other purposes, including transportation. There's this other problem, right? Is now if we want to electrify vehicles, people tend to arrive home in the evening and plug in and charge, which actually makes this ramping problem worse, right? It'll increase demand and then it just worsens the problem. Also, if it's charging overnight, this is the time of day where emissions are the worst. So if you come to California, you rent a car, please don't charge in the evening, because it's when emissions are the worst. If you have a chance, try to do it in the middle of the day here. So obviously there's an opportunity where can we control EV charging, shift it to these times, away so it doesn't exacerbate this ramping problem, and minimize the marginal carbon emissions. Here's actually what I want people to do. And by the way, this is kind of California specific. I want you to leave home with 30%. Did anyone leave their home this morning with 30% charge in their phone? No? Yeah? Yes, Laura, thank you. Yeah, you can charge in your desk, right? Yeah, okay, good. You can live in California. So that, perfect. Because, that's when carbon emissions are least, and if you have an opportunity to charge in the middle of the day, you can return home with 90%. You don't have to worry about charging, in the middle of the night. And by the way, that addresses inequities where people might not be able to charge at home if they don't have a place to park. So, okay, now that's all of the context which I want to use to describe this project, SlrpEV, about improving public and workplace charging, because we don't have sufficient public and workplace charging. So the goal here is to create the next generation of workplace or public EV charging that achieve these goals here. What I want to emphasize is this is a deployment where we built an EV charging station, and there's many smart EV charging stations that optimize power delivery. So why is this different? This is different because we're not just optimizing the charging schedule, the power, but we're optimizing the price that we offer people, and we show people a menu of prices with different options. And so really, this is about putting the human in the loop with machine learning to understand their behavior, as you'll see. So I like to think about this as a cyber-physical human system. So let's talk about the cyber and the physical. So the physical is we have this garage with these level 2 chargers that are 6.6 kilowatts each, right? You can go there and charge. And the way it works is as follows, and I'll describe the cyber, the software part. So you pull up, you scan a QR code, and then there's an app or a web app. You log in, and then you get prices. Don't worry about the prices and the options yet. I'll explain that. You consider these options, and then you pick your choice. That choice goes in, and then there's some sort of optimization that's happening, and it sends a power schedule back down to the chargers, and then there's the so-called metrology data every 5 minutes, we get an update from the chargers of how much power it's delivering, whether someone's connected, yada, yada. So that's the cyber part. Now, the human part, I'll describe in a moment, but first, some usage statistics over this period up here. So, energy, charging sessions, unique users. Here I'm showing the energy and sessions by month. Actually, what I want to emphasize here is the most important metric, I think, is the number of unique users, because then we get unique behaviors of how people arrive and depart and the energy they need and the choices they make. So I think that's the most valuable metric here, is actually getting a lot of different unique users and different behaviors. And there's seasonality that we find. So people use this as commuters, basically. So here's a nice visualization where you have day and hour on the x-axis. So Monday, Tuesday, Wednesday, Saturday, Sunday, there isn't much usage. And then we have month, so you can see the seasonality. And basically you see people use this as workplace charging. Monday, Tuesday, Wednesday, Thursday, Friday. And if you look a little closely, it's a little lighter in summer because there's less activity in campus, and it's kind of heavier in the beginning of our terms. So now the human part, which is really the key unique thing about this research. So it's really about providing choices, discrete choices. There's discrete choice theory underneath this. So let me describe the two choices we offer our users. The first is called regular, and this is your normal charging experience with a phone or a laptop. You plug in and it charges immediately at full power until you top off the battery or you unplug. Okay, regular. The more interesting, okay, so in regular, we consider it not controllable. Like we can't change the power delivery. The more interesting one is scheduled. So with scheduled, we ask them, what time do you plan to depart and how much range, added range you need? Like how much energy do you need? So this provides constraints in an optimization where we know, okay, they plugged in, we need to deliver to them this much energy by this deadline, but the trajectory of the power delivery is otherwise flexible. Yeah. And so this is now controllable. So the research question is, if I want to shift load, how much do I discount scheduled to acquire this flexibility? By the way, this is not strange or different because when you shop on Amazon, you experience this. You get shipping options, right? There's next day shipping, normal price, and then there's like the Amazon delivery day, right? Where it's discounted and, so you give up some quality of service in some sense, if you don't mind, and you get cheaper shipping price, but they're optimizing logistics on their back end. Yeah, so we're like the Amazon of EV charging here. So that's the idea. So the question is, how do you do this? Now, okay, we didn't just write we first wrote some papers and then we got some funding to build it and do it. And I was concerned, like, okay, are users actually going to stress out about picking regular and scheduled to save 40 cents per hour? Are they actually going to stress out about this each time they charge, or are they going to like not care and just always pick regular? So, to save like $1 or $2. So it turns out that actually people really do pay attention to this, at least at UC Berkeley. I don't know how this will translate in other places. But here's how we model it. So we use discrete choice theory. Some of you may be familiar. Actually, Daniel McFadden, economist, coincidentally from UC Berkeley, won the Nobel Prize for this concept in the year 2000. And the idea here is that each choice, index J, has some utility. And because this is econometrics, they love everything linear regression models, which depends on controllable attributes Z, like the price. I can control the price. And it also depends on attributes W I can't control, like when they arrive, do they have a charger at home? How much energy do they need? And then there's these perception errors because humans aren't robots. Their decisions are not optimizing an explicit utility. There's some randomization. Okay, so this is classic stuff in transportation economics. If you assume the error has some distribution, you get this logit model, you get this form where the probability of choosing regular or scheduled follows this kind of softmax-like function of V, which is affine in these variables, where Z, I'm going to optimize the price. Okay, so the mathematical structure is a little important here. By the way, many of you are transportation associated, so maybe you've heard of discrete choice theory and behavioral economics. This is a classic idea, of course. In machine learning, it has another name. Anyone know the name in machine learning? MDP, Markov decision process. It's not what I'm thinking of. It's just logistic regression. So I think machine learning people, when they learn about classification, they learn logistic regression. I think machine learning people have no idea that this is also discrete choice theory. I think people who really work in discrete choice theory, they all know this is logistic regression. So anyways, funny how some fields know about each other and other fields don't know about each other. So anyways, we optimize price and power, which are the variables z and u. And there's some interesting mathematics that'll just give you a brief idea of is that actually there's some optimization theory you can do, which is kind of cool, where if you're minimizing the expected cost, where it's the expectation over the probability of choices index j, it has this kind of format. And it turns out that this would seem to be a non-convex, nonlinear problem. But it turns out that you can reformulate this where it's multi-convex, which means that you can freeze all the variables but one, and it's convex in that optimization variable. And then you solve with respect to that optimization variable, freezing the others. And then you rotate, you kind of permute, and then you freeze the other optimization variable, solve with respect to the next one, and you kind of do a round robin thing. They call that multi-convex. So it's still nonlinear, non-convex, but this allows us to solve in real time. So you can refer to this paper to see some of the mathematical details. So, in the end, here's what you get. So we optimize price, and here's the result. So we have hour of day, and what I want to focus your attention on first is the green curve. This is the utility time of use, TOU, time of use price. This is what the electric utility charges us. So the key point is that certain times of the day, it's very expensive. And you kind of already know why the late afternoon and early evening is more expensive, because that's when the ramping happens. It's very difficult for the power grid to balance. So basically, we just want to avoid EV charging here. Meanwhile, if people arrive early in the morning, if we can delay their charging just a little bit, maybe we can dump them into the lowest cost period. You can start to see what's going on. So here are now the prices for regular and scheduled in yellow and purple respectively. And actually what you can see is they're kind of the same price, because many times of the day, I don't really care what choice they pick. I just want to get them charged and out of there. Yeah? So it's sort of like an aggressive American restaurant where the waiter says, get you fed, you want your check, take your check, get paid, get you out of there. Right? So that's what we want with EV charging stations, usually to increase utilization. And because when we pump out kilowatt hours, then we can make revenue to recover the capital cost. However, we can also reduce the operation cost strategically if we, at certain times, dynamically discount scheduled. So I'm actually going to highlight the morning. It's kind of the more important one because that's when everybody's arriving to work. What you can see is the price drops at 9 a.m., but we kind of discount a bit the price that comes out of the optimization to try to incentivize people to pick schedule, because if they pick schedule, they get lower price, and we basically delay their charging and dump it into this low price period. That's kind of the intuition of what all the mathematics and learning is producing. And in the end, we get this. So we compare to a baseline of $1.50 per hour compared to optimizing the price and the power. And this is only optimizing the power, just fixed price to users. And we can actually increase the net revenue by almost 50%, which is a combination of reducing the operating costs, but also we kind of learn from data from user behavior that we can actually charge a little higher price and people will still use. So we're also learning what is people's threshold for paying for charging service. Okay, and then here you can see how we've got these different price periods. We want to charge in the super off-peak. We want to avoid the peak. And here's the mean power over a period of SlrpEV, where you can see just before this green period, you can see that when it's optimized, we basically, just before, we kind of bring power almost to zero because we're basically delaying those users and dumping them into this period. Yeah, so, but this happens all dynamically by learning user behavior and then optimizing with respect to the utility tariffs. So this was me. I thought this actually worked in practice, which I was shocked. I thought people would not be sensitive to small variations in price. But they actually were. So that's pretty cool. All right, let me move on to NEXTCAR, and we're going to talk about automated and connected vehicles. So, this NEXTCAR project sponsored by SlrpEV, the goal very simply is to reduce energy consumption in vehicles by 30% by leveraging connectivity and autonomy. And so this is collaborative between my lab, Francesco Borelli, the MPC lab, and a startup that's spun out called WideSense. And these are our vehicles that we use for the platform. We're actually in the 7th year of this project. I really want it to end, to be honest. And most of our experiments were on this with this car on the left. Now, one way to reduce vehicle consumption by 30% with connectivity and autonomy is to start with a baseline vehicle that's already very inefficient, right? Now, in 2017, if you go to the EPA website and you downloaded all the vehicles and you sorted it by highest fuel economy to lowest fuel economy, you know what the #1 vehicle is and best fuel economy? Is this one. We literally picked the hardest car that you can buy in America. Okay, it wasn't on purpose like that. It's because we had a strong partnership with Hyundai. But yeah, we realized later, okay, we made it pretty hard for ourselves. Of course, the people at DOE were like, good, Scott, good. So they like that. Okay. And then we moved to a full battery electric, this Ioniq 5. So we developed all these different technologies: fleet dispatching, highway driving, urban driving, parking and charging. I'm only going to talk about urban driving, and this eco-driving through signalized intersections with this AI-enabled motion planning and control. So here's the key idea, and some of you may have seen this if you've worked in this field, is eco-driving really refers to the idea that there's connectivity between the traffic signals and the cars, specifically the traffic controller that knows the signal phase and timing, that is, if it's red, green, yellow, and how much longer it's red, green, or yellow, it wirelessly transmits to the vehicle, and the vehicle optimizes its speed trajectory, okay? Now, this is not rocket science if you want to minimize energy. You know what the optimal solution is if you want to minimize energy for the speed profile? I was going to say ride your bike. Yeah, even better answer. He said stay home. I like that better. Good. Okay, we all have good, same sense of humor here, so that's nice. Yeah? So, okay, but if you need to go from A to B under time constraint, because if there's no time constraint, then you just don't move, but, you know, then it's just constant speed. But the problem is that you have these red lights. So if you can get this information, it's very helpful. So just to motivate, here's a simple, just to motivate the problem. Here I've got 3 different algorithms or models: intelligent driver model, minimum time, minimum fuel. So intelligent driver model is like how a human drives. Minimum time means I'm trying to get from my origin 0 to my destination 800 as quickly as possible. So I want to minimize my position along the vertical axis, you know, without going through these red lights. Anyone drive like this? Well, they're kind of slamming on the accelerator as soon as it turns green, and then immediately braking, you know, once it turns red. Miriam's a very good driver. She does not drive this way. I can confirm. She's an excellent driver. Okay, and then the minimum fuel strategy is like this. You can see it's kind of constant speed, right? It's this linear thing. But this should make you nervous. Why does it make you nervous? You're running, so if I'm driving the car and you're in the passenger seat, yeah, you're going full speed and it's still red, right? And it's not slowing down. Even though you're seeing red, you anticipate, okay, I should come to a stop. Because, you know, here it deterministically knows it's going to turn green the moment I arrive. Okay, but this feels risky, no? Yeah, okay, so not robust to this uncertainty, yeah? So we worked a lot on this. We gathered data on traffic signal timing, made probability distributions. This was interesting that it was bimodal, you know, in this intersection. Rush hour had this, you know, second mode, which is longer delay. And then we use recently developed methods in OR that use data-driven distributionally robust optimization, where we can be robust to an uncertain distribution of the delay using data acquired from driving through these intersections. And then we're more conservative. So you can see it's not flying through the intersection the moment it turns red. And this blue represents like the probability distribution of the delay. So that really helped it make it like more comfortable for real world. And then we actually deployed it or demonstrated it. So here's what it looks like. And this was like almost 7 years ago. So this is kind of an old video. I'll show you newer ones in a sec. But you can see here on the right, it's connected to the traffic light. It's red. Here, the traffic light is red, and it shows a countdown timer. Yeah, and then once it turns green, you'll see it drive forward. Now, this is the longitudinal motion is automated. So the reason there's a camera at the foot is to show foot's not touching the pedal, right? So there's longitudinal automation, and this one is laterally controlled by the human with the steering wheel. I'll show you how we get rid of that in a movie later. So you can see here how it connects to the intersection, and then when it passes through this intersection, it'll then try to connect to the upcoming intersection. This is in Southern California, in the city of Arcadia, a street called Fair Oaks, which is deployed with these, they're called roadside units, which wirelessly transmit the traffic signal timing. So there it connects, and you can see, and it can optimize its speed trajectory. Okay, then we took it up one level. For level 4 vehicle with lateral motion, we tested it at a site that's something like what's being the acronym for the automated testing, IACT. Yeah, I think it's something like what IACT is and will be, this automated vehicle testing site in the Bay Area called Momentum, where we made a mixed reality environment, virtual environment, and I'll just show you the video. So what we're showing here is the next level where we now have automated lateral motion, of course. And then it's this is also showcasing our mixed reality testing, where there's virtual traffic lights here, and then it's interacting with other vehicles. These, our vehicle is the red one, and then we have these virtual vehicles. We call them NPCs, non-player characters, right, from video games. These are the NPCs. So actually, what happens is this one gets, I think the Cybertruck gets stuck, in this red light. Yeah, and then our vehicle here stops like further behind the Cybertruck as a virtual vehicle, so it also interacts with the traffic. Okay, so then we could show under the right conditions, we can improve vehicle energy consumption, and then SlrpEV said, all right, you guys did a great job, and so now we're going to burden you more and ask you to do difficult things. And take everything you've done in California and put it on trucks and bring it to Washington, D.C. at the SlrpEV Summit, and then do a demonstration, basically create a Disneyland ride at this conference in the terrace of the convention center here in Washington, D.C. So we did a big demo. Here's a picture of us. That's Jennifer Granholm, the Secretary of Energy, Pete Buttigieg's best friend, right, up in the federal government. And here's what the video looked like. So very picturesque at this conference, actually, very beautiful along the bay. But anyways, the students, like many of you here in the audience, basically created this in like 4 weeks. It was incredible. Where we made kind of a half moon shape track, and then we made a virtual environment, and then we had our NPC vehicle in red. And the virtual traffic light. And then what's being showcased here actually is you've got the ego vehicle that's communicating with this virtual traffic light. And the other thing that'll occur as this plays along is you'll see that it's also doing automated lane change for the purpose of reducing energy consumption. So if it determines that it would be best to do a lane change to go around this NPC to reduce energy consumption, it'll go ahead and do that. So I think that shows as this plays. Let me just skip that. And then the final thing I'll show you, and I won't explain any details, is we took that to a next level to do platooning, where now we have this automated vehicle platoon. The lead car is blue, and then the 2 following cars are white, and you can see them all move in synchronization. So the lead car is communicating with the traffic light, and then there's vehicle-to-vehicle communication between these vehicles to maintain constant headway, also for the purpose of reducing energy consumption. So, for highway and for trucks, there's been a lot of work at PATH doing this, some mixed results. And here we try to explore what is the possibility to do this on arterial roads with light duty vehicles. So I want to give a lot of time for questions if we have. Okay, key things. Transportation produces 40% greenhouse gas emissions in developed economies like California. Next generation charging stations, we need to use human kind of human behavior, and AI is a very nice tool, machine learning, to understand human behavior, so we can really optimize power and price, so we can make workplace charging economically feasible, because it's not really economically feasible today. And then I also talked about how connectivity and automation, I think primarily the purpose is safety, honestly, but also there's a secondary purpose that can focus on reducing energy that we focused on. And if you find any of this interesting or find opportunities where we can do something together, please reach out to me so we can collaborate on reducing transportation CO2 and just create really creative, exciting innovations in mobility. So with that, I'm excited to hear any questions you might have.
Thanks for the presentation. We have time for one or maybe two questions.
I have one quick question. Thank you, Scott, for a wonderful presentation. Regarding your previous the charging experiment, so you guys also looked into how does that impact the overall behavior of the people? Because I'm thinking like one of the biggest things that challenge they had in California was finding an open like charging spot. Like if I every day see those eight charging slots are full, maybe I just take my Tahoe to work next day, right? So like hugely negatively impact like the whole emission, the whole idea. So we looked into that.
Yeah, we did look at how it changes behavior, particularly around arrivals. So I haven't shown it here, but we have a paper where we tried to disincentivize people from arriving and charging during the peak period. And so actually, in the study I showed you here, we consider arrivals as like a Poisson process, independent of price, which is not true. So I think a better way to think about this is almost in a game theoretic way, where people react to the price, not just from what choice they pick, but how they arrive. And so we have a different experiment that we did. And indeed, people, if you publish to them the price a priori for every hour of the day, then they actually do react, and they'll shift a little bit their arrival within their schedule. So I think that also is another huge benefit to help with congestion. So we started that, we demonstrated it here, but I think there's potential to really scale that out more. I mean, Tesla, of course, with their superchargers, they already have some time of use pricing. And I've seen in Los Angeles, like in Pasadena, I'm thinking, you will see all the Uber drivers like line up at the charging station right before it turns 11 p.m. and then the price drops and then they all start charging. So short answer is yes. And I think there's potential to really deploy this more systematically.
Oh, thank you so much for such engaging presentation. I have a very similar question. And do you see any special behavior in the schedule option of charging? Because how is that fair that I can suggest or request maximum power to charge as fast as I can, while other person may require less power and still we are charged the same? Because you had a fixed rate for that, right?
Yeah. Fairness is a very complex issue, right? So I think it really is analogous to that Amazon example. You can think about it as I will take a lower quality of service product in the sense of not receiving it immediately for a discounted price, right? So they're different products in a sense in terms of quality of service of the delivery timing. Now, something that gets a little more complicated in fairness is that we have a behavior model, one behavior model for every user. You could make this really specialized where you could have a behavior model and differentiated pricing for each individual user or even categories of users. But that would be illegal because then you would literally be providing regular and scheduled that is differentiated by category of user, and which is the equivalent service ultimately, but then maybe because you have some individual data or at least group data, you're trying to optimize to sort of incentivize a different behavior from them. So the issue of fairness is complex, but the short answer is to think about the service as not just energy, but timing of the delivery of energy.
Thank you.
1 minute for one more question. Okay, you can have it.
Yeah, thank you for the presentation. Very interesting. And your analogy to a restaurant had me thinking this, and it ties into both the previous questions. Any incentive or disincentive to, not stay on the charger beyond charging time because you're losing revenue and you're decreasing your net benefit to the system?
Yeah, the quick answer is when they pick schedule, if I were to redo this, I would do it a little different. But if they pick scheduled, when they indicate the departure time of 1 p.m., if they stay after, then the price increases. We call this overstay price. Tesla, for example, gives it an idle time. We get them to commit ahead of time, right? Of when they plan to leave and they stay after, then the price increases a lot. So that works. Also, charging per hour is a big deal because you're not just providing electrons, you're letting them rent atoms in space. And there's a value to that service, right? Because I think largely people want to park. And secondarily, if they can get a charge, that's great. So you actually have to consider both of those.
That's a really quick question.
Sorry, it's really quick. I want to add to earlier questions regarding the choices of people. I felt like actually, I wonder if this is at work, right? Essentially, people do have a choice of not charge at all.
Right.
Then that's actually a big indicator of their behavior. And also, you actually only observe those people who do choose to charge.
Yes.
These people may do not care about money as much as those people who choose not to charge because they don't.
Yes.
Right? So I was wondering if maybe that's something that can be addressed also in maybe a follow-up study that you're carrying out.
Yeah, Professor Yang, as usual, you've put your finger on like one of the most difficult, important issues that I didn't. So there's actually 3 choices: regular, scheduled, or don't charge. And so you also have to consider, and you want to measure how many times someone decides, I don't want to charge, but we can't observe that. Time's up, so I'm going to leave that there. But I can tell you, yeah, that's difficult. I can tell you, yeah, afterwards, if you want to know, I can tell you.
Thank you so much, Professor Moura.